Hello, chemistry students. This is your Unit 9 lesson on double replacement reactions. So, double replacement reactions have a specific format or pattern. They involve the mixing of two soluble ionic compounds. Soluble means that the ionic compounds will dissociate or dissolve in water. So AB represents one ionic compound, with A being the cation and B being the anion, and CD represents another ionic compound, with C being the cation and D being the anion. Now, what happens when you mix these two things that are dissociated in water? They switch places. They double replace. So cation A replaces cation C in this compound, and cation C replaces cation A in this compound. And you can see then the products become of AB and CD become AD, because outer, and then inner becomes CB. All right, so they switch places. Now, let me give you an example. It might be easier to see this pattern. So it makes it really easy to predict the products of a double replacement reaction. So here's an example. Silver nitrate, which is a soluble, one that will dissolve in water, ionic compound, and sodium chloride, just salt water, which you know dissolves or dissociates in water, and that's what the AQ, are kept separate. When they are mixed together, silver replaces sodium and the compound forms, it's called silver chloride. So outer, and that happens to be something called a precipitate, a solid that forms. And then the inner, the sodium, replaces the silver to give you sodium nitrate. And again, you end up with a compound, however, that is aqueous, that is soluble. So you're actually able to take out the silver chloride because it's a solid that precipitates out. Here's the reaction. Again, you can see the outer inner works. Silver goes with chlorine. And again, we don't have to worry too much about the balancing because silver, nitrate, sodium, and chloride are all +1 and -1 ions. So they all go together with a 1-to-1 ratio. So silver replaces sodium. And so outer would be silver chloride, and inner sodium replaces silver. Inner would be sodium nitrate. And this would be your balanced reaction. Let me just show you a brief video on what that looks like. So what you can see here in the video is two solutions of sodium chloride and silver nitrate. They are separate. And then this is just the silver nitrate. And they're going to add, they're going to mix. Sodium chloride is added, and you'll see this white precipitate forming. This white milky solid that is the silver chloride is forming. And you can see it's precipitating down, it's falling down to the bottom. And you're going to get this white solid that eventually you'll be able to filter out. And the leftover, the sodium nitrate, is just still dissolved in the solution. So we're going to work a lot on predicting products and deciding which is the precipitate in this lesson. Okay, so double replacement reactions produce a precipitate. A precipitate is a solid that forms as a result of changes in solubility of a new product that has formed. Okay, this is a sign that a chemical reaction has occurred. All right. So let me give you one other example that you can kind of see in pictures. Double replacement reactions produce a precipitate. So here are two aqueous solutions. One is potassium iodide, that's the one right here. The other is lead nitrate, that's the one here. You can see they are dissolved or dissociated in the water solution. You can't see them because they're floating around. Now we're going to mix them. We're going to combine them. We're going to actually do the reaction. And what happens when you put these together is that the lead and the iodide actually kind of like each other. They're very attracted to each other. So they form a solid precipitate. And that's what this yellow is. And you can see if you let it settles to the bottom. We could actually filter out that lead iodide. So the products of this reaction are the sodium nitrate, and that's this. It's still soluble, it's still dissolved, and the lead 2 iodide. That's the ionic compound. And you can see that for every one lead, we have 2 iodides. Okay, so that's the ratio in this particular ionic. That's why, unlike the one I showed you, there are some coefficients that are needed to balance this equation. But one of the products of a double replacement will be a solid that we can actually filter out, and that solid is called a precipitate. All right, so going on, let's make sure we understand the terms I've been using. Solubility of a salt depends upon the type of ions in the salt. Some salts are soluble in water and others are not. An aqueous solution, so you want to make sure you know this, is a solution with water as the solvent. And a compound is said to be soluble if it readily dissolves in water and does not precipitate if left undisturbed for an extended period of time. So I can put sodium chloride in water, stir, and it will say dissolved, or as we said, dissociated into its ions. Now, what is soluble versus insoluble? Ionic compounds that dissolve in water are described as soluble. So you all know sodium chloride, salt, dissolves in water, dissociates. So an example of an ionic compound that dissolves in water is sodium chloride, or another one would be potassium nitrate. We're going to learn how we know this in a couple of slides. When these compounds are mixed with water, they dissolve, and we describe them as aqueous. Now, ionic compounds that do not dissolve in water are described as insoluble. For example, the compound magnesium hydroxide, or as we saw in the last slide, lead 2 iodide, are insoluble. An insoluble substance simply remains in the solid state when added to water. So you add it to water and you can stir and stir and stir all you want, but that substance will not dissolve. All right, now there's something called solubility rules. You can predict whether a precipitate will form in an aqueous reaction using solubility rules. These are the solubility rules. Soluble means they will dissolve in water, and they will be AQ. Insoluble means they will not dissolve in water, and these compounds are the precipitates. Now, you don't need to memorize these rules. Are you listening to me? You don't need to memorize these rules. What you do need to do is be able to use a table like this. So for example, this says compounds containing the following ions are generally soluble. So if you have group 1, that's alkali metals, guys, lithium, sodium, potassium, and ammonium in an ionic compound, they will all dissolve. There are no exceptions. Same thing with these anions, nitrate and acetate, pretty much no exceptions, very few. Now, chlorine, bromine, and iodide are also generally soluble unless there are exceptions. If they are paired with silver, mercury, or lead, they are insoluble. So for example, we saw that sodium chloride was soluble, but silver chloride was not. And sulfate, when paired with strontium, barium, lead, silver, or calcium, are insoluble. So sulfate is mostly soluble, but not entirely. Now, these ions are generally insoluble, although there are always exceptions. And the exceptions usually have to do with group 1 and ammonium. So sulfides generally do not, you can't get them to dissolve in water unless they are with group 1, ammonium, or some of the group 2 ions. Hydroxides are generally insoluble unless they're paired with these cations that are soluble. So you're going to have to use these rules. Now, carbonates, phosphates almost always are insoluble. That means they don't dissolve unless you are pairing them with these group 1 and ammoniums. So there are definitely some patterns, and you're going to do an exercise to look at those patterns in a few minutes. All right, so we're going to practice here. See if you pause the video and see if you can classify the following compounds as soluble or insoluble. You've got silver nitrate, sodium chloride, silver chloride, and sodium nitrate. I think we've seen these before. All right, so as you can see, silver nitrate, if you look here, you can look at the nitrates, okay? There are no exceptions. All nitrates are soluble. So since we've got nitrate, it's got to be soluble. Now let's look at this one, sodium chloride. Well, we've got chloride and we've got group 1 sodium, but let's look at the one that says no exceptions. Any group 1, any alkali metal is going to be soluble. So this one's soluble. Okay, now we've got silver and chlorine. Well, I don't see anything about silver here, but I do see something about chlorine. So I'm going to look at chlorine, and it says when paired with silver, it's insoluble. So that is our precipitate. It's insoluble. And then finally, you've got sodium nitrate. Let's check. Well, this is an easy one because sodium is always soluble, as is nitrate. So sodium nitrate is soluble. So again, here's that full reaction. We saw this before in the beginning slides. Silver nitrate and sodium chloride form silver chloride and sodium nitrate. You can predict the products of this. Silver goes with chlorine, sodium goes with nitrate. Then we just have to go to the solubility table and see if we get a precipitate. And we do, because silver chloride is insoluble, and here it is precipitated on the bottom. That's called the full reaction. So let me just emphasize something. This is called the full reaction. We see all of the compounds as compounds. Their states are indicated, but we don't see them dissociated. Okay, so now there's another term you need to know, something called the complete ionic equations. A complete ionic equation is an equation that shows dissolved ionic compounds as dissociated free ions. So here was our full reaction. We know the silver nitrate was aqueous. We know the sodium chloride was aqueous. We know this was a solid. We know the sodium nitrate is aqueous. Look at the difference here. Here is the complete ionic equation. So instead of just saying aqueous, we show that the silver and the nitrate are dissociated in the solution. We actually show this picture, okay? And we also show the sodium chloride is dissociated in the solution. We actually indicate this. It's not floating around as a molecule of some sort. It's floating around as sodium and chloride ions. Okay, now let's look at the product side. Now the silver chloride we have determined is a precipitate. It is not floating around in solution. But the sodium and the nitrate is an aqueous compound, so it is floating around in the solution. So as you can see, oops, let's go back rather than forward. As you can see here are the products. We've got this solid silver chloride. It is not floating around in the solution. We have an aqueous solution of sodium and nitrate. They are still dissolved in the water. When the silver and the chloride get together, they're so attracted to each other that they form this precipitate and they will not dissociate or dissolve. However, the sodium and the nitrate are not attracted to each other enough to form a precipitate. So they remain dissociated. They remain dissolved. All right, so this is the complete ionic. Notice how we write it. We break them apart. Anything that's aqueous, we show as ions. Anything that is not aqueous, we leave as the compound and make sure we have S next to it. So that's a complete ionic equation. Now we have to define something called a spectator ion. A spectator ion is an ion that is present during a reaction but does not take part in the reaction. An ion that appears on both sides of an equation and is not directly involved in the reaction is called a spectator ion. So notice something. The sodium, oops, there's the sodium, and the nitrate are the same on the reactant side as the product side. They are aqueous and aqueous. Nothing changes. They are known as spectator ions. They are watching the silver and the chloride get together, but they themselves are not changing. So they are spectating. They are not directly involved. So we identify the spectator ions. And that leads us to something called a net ionic equation. A net ionic equation is an equation that only shows the ions that undergo changes during a chemical reaction. So the spectator ions are omitted from a net ionic equation. The net ionic equation for a reaction solution that shows only those particles that are directly involved in the chemical change. So notice the difference between complete ionic and net ionic. We do not include the spectator ions. Nitrate and sodium don't change, so we take them out. What does change? Well, in the beginning we had aqueous silver and aqueous chloride, and at the end we have the compound silver chloride. So you're going to do an exercise to really delve into this and learn it in just a few minutes. I hope these notes have been helpful, but once you finish these notes, please indicate that to me, and I'll come over and give you the next assignment. Thanks for listening.